All right, our third value theorem of the semester, we have the intermediate value theorem. We just talked about the extreme value theorem, and then this is going to be hopefully a short video going over the mean value theorem. The mean value theorem is normally proved actually through Rolle's theorem. Rolle's theorem is going to be just a very specific case of the mean value theorem. It's not that important in and of itself by a standalone thing, but it's going to be easier to prove, and then it's going to be easy enough to extend it and see how the mean value theorem falls out of there. So we'll focus on Rolle's theorem a bit in the proof only because that's an easier thing to prove, and then hopefully, again, you'll see the extension to the mean value theorem. The mean value theorem is an important, interesting concept in and of itself, but we're going to use it to prove a pretty big, important result. There's other important results that you can prove using the mean value theorem. There's two others that I can think of off the top of my head that'll be important later on that maybe we'll come back to and prove using the mean value theorem. But at the very end of this video, we're going to give ourselves a bit more of a leg up on what the first derivative is going to tell us about. Anyways, here's Rolle's theorem. Let's pretend that we've got some continuous function on a closed interval, and it's also differentiable on the open interval. We don't care about the derivative existing at the ending points. We could talk about one-sided differentiability and have that, but we don't really care. And then we also have that the ending points are the same height. They have the same y value. Then Rolle's theorem says there's at least one c in our interval. There's that notation again. This means essentially that like c, oops, I want to use, oh, that's fine. I'll use green. C is like in between these things. So somewhere in this open interval such that the derivative is equal to 0 there. Essentially, we're saying there's one spot at least where we're going to get a horizontal tangent line. So let's go ahead and just draw this, get our intuition fine. I'm going to first start with the ending point bit. I'll draw these 2 points that happen to be the same height approximately. I'm not going to put a scale or an axis on here. Who cares? And then I'm just going to make a continuous function that's differentiable in between here. So that means no sharp corners. Everything's going to be connected. There's no vertical tangent lines. So it's going to be a nice, smooth, kind of polynomial-looking function. That'll work. Not terribly smooth because my drawing isn't that great, but oh well. And then here, if we just go to our little result, we can see 2 spots, 2 points here in this case that have horizontal tangent lines. So this is what Rolle's theorem is saying, is that if you draw a continuous function that's nice and differentiable on these from one ending point to the other, and the ending points are the same height, then we're going to be able to find a spot where the derivative is equal to 0. We're going to prove this by splitting it up into 2 cases. Our first case is that we're just going to consider a constant function. This is going to be our easiest one because we know that for a constant function, the derivative is 0 everywhere. And our next case will say, well, what if it's not a constant function? Now, we're not actually going to say case 1 is a constant function, case 2 is not constant. We're going to define it a little bit differently. If you go back to the beginning of this thing, notice you've got a continuous function on a closed interval. The extreme value theorem can kick in. And remember, the extreme value theorem guarantees the existence of both the absolute max and the absolute min of our function on this interval. So we know, it might not be important for us, but we know that there's an absolute maximum of f on this interval a to b, and there's an absolute minimum. We also know where those things show up. They show up either at the ending points of our closed interval or at the critical points. That's what we saw last time. So what we're going to do is we're going to say, instead of saying that this is a constant function in our first case, we're going to say, well, what if the ending points are both the absolute max and the absolute min? And then in case 2, we'll say, well, we know that there has to be both of the absolute extrema here, max and min. What if at least one of them is not the ending point? So one of them is actually in the open interval. So here, case 1, we can say one of the ending points is the absolute max and one of them is the absolute min. But remember, in Rolle's theorem, we said that both the ending points are the same height. So if one of them is the max and one of them is the min, then both of them are the max and min, meaning we've got a constant function. And in case 2, we'll say there's some other absolute max or absolute min, who knows which one, somewhere else outside of the ending points. So here we go. Let's prove this stuff. So case 1, suppose that f of a and f of b are both absolute max and absolute mins, then f is constant. Then, if f is constant, the derivative is equal to 0 for all x values in that interval. So if you wanted, you could add a line that says pick any x value in a and b and call it c. Then f prime of c will equal 0. And remember, we just wanted to show that there was at least one spot where the derivative was equal to 0. And we found an infinite number of them, but then we can find one. You can just pick any of them. So that's the really, really easy case. If you have a constant function, it's not a big deal. If it's not constant, though, then what we have is we're going to say, suppose at least one of the absolute extrema occurs at some point c in the interval, essentially not an ending point. Then our function's not constant. It's going to end up looking like something like, oops, I want this to actually be the same height, something like that. Anyways, all this to say, we know that there is the other absolute extrema. There's one of them. Since it's not at the ending point, we know it has to be a local extrema at a critical point. So that was one of the things that we saw earlier, that absolute maximums and absolute minimums show up at critical points or ending points. So if it's not at an ending point, it's at a critical point. And if it's at a critical point, then we know that f prime of c, oops, that's supposed to be a c, not an x, is equal to 0, or f prime of c doesn't exist. That's the definition of a critical point. But we were told right at the very beginning, hey, our function's differentiable on this open interval. That means that the derivative exists. So the only option is that f prime of c is equal to 0. So we're not sure where this point is, but we know it exists by the mean value theorem. And so we'll just say that's the point. So that's the proof of Rolle's theorem. All that to say, Rolle's theorem says if you have 2 points that are the same height and you connect them with a nice, smooth, continuous, differentiable function, then you're going to get at least one point where you've got these horizontal tangent lines. Now, the mean value theorem is the exact same thing, but what we're going to do is essentially tilt this. We're going to say, what if the points aren't at the same height? Then clearly we don't have this horizontal tangent line thing. But if you take this picture that we drew and you tilt it, then the tangent lines that we've drawn are right here. Oh no, this is bad. Here we go. That's a little better. There, and there's another one like there. And notice that they're not horizontal. The derivative here is not equal to 0 at these points. But it's going to follow this same line that connects the dots. So here, if we draw a nice horizontal line connecting our ending points, then our derivative is horizontal as well. But if our ending points aren't the same height, then this line connecting them is not horizontal, but our tangent lines that we had were still parallel. So here's the mean value theorem. It's a little bit different, but it's the same thing. We're not going to prove it. The only reason we care about Rolle's theorem in our class is because it'll give us some intuition about the mean value theorem. It's a lot easier to visualize. Anyways, let f be a continuous function on a closed interval still, and it's differentiable on the open interval. Then there's still at least one point in that open interval where something happens. But now, since our points at the ends are not the same height, it's not necessarily true that the derivative is equal to 0. But now the derivative is equal to this f of b minus f of a over b minus a. Notice that this is just an average slope. This is the average rate of change between the 2 points. Difference in y over difference in x. Also notice that for Rolle's theorem, when we said that f of a and f of b are the same thing, the slope between those two lines is 0. So it wasn't anything special about the derivative equaling 0 other than it's easy for us to visualize it. So the mean value theorem really says that the instantaneous rate of change is equal to the average rate of change at this point. Visually, that means that the tangent lines that we're looking for are ones that are parallel to the secant line connecting those two things. So again, if you've got, maybe I'll draw a set of axes here, and we'll actually get an honest-to-goodness function on here. If you have some point here and another point up here, and we go ahead and draw some kind of like parabola type shape connecting the dots, then sure, there does happen to be a horizontal tangent line somewhere in here, but that's not the spot that the mean value cares about. Or sorry, the mean value theorem cares about. The mean value theorem says that if you draw a line connecting these 2 points, you can find a point on the graph where the tangent line is parallel. And it looks like right there will do it. So we've got some point right here, it looks like, where the slope of the tangent line is the same as the slope between these two ending points. That's what the mean value theorem tells us about. So we can use the mean value theorem to do some stuff, but I want to give you another example of this. This is just a kind of wordy, talky version of this. Let's say you're driving on a tollway. Let's say you're driving on like 294 or something like that. And you drive through a couple of tolls. If you have an I-pass, then you don't stop to pay the tolls. You just drive right through. And when you drive right through, you have this little device that kind of like senses that you've gone through the toll, and then it'll automatically deduct the however many cents it is to go through that toll from your account. Then you can have your account like auto replenish and blah, blah, blah. Hopefully you guys know how tolls work if you've driven on an interstate before. So that's that. On your online account, and this is actually true, you can look this up. When you drive through a toll, it time stamps it and it gives you the toll location that you were at. So you can go through and see like a history of when exactly you drove through each specific toll. And you can look those tolls up. They have exact addresses, and you can look them up on Google Maps or something like that and see exactly their location, which also means that if you really wanted to, you could see the driving distance in between any two tolls. Okay, so let's imagine this now fictional situation where I'm driving through a bunch of tolls, and let's say I go ahead and I look up my history and I see that I drove through two tolls that were 10 miles apart, and it took me, I don't know, 10 minutes to get through there, right? Then I know that my average speed was 60 miles an hour in between. I went 10 minutes for 10 miles. That's a mile a minute, or 60 miles per hour. Cool. So that's my average speed. That's this right hand of the mean value theorem equation here. What I know is that since my movement is continuous and differentiable in a car, that if my average speed or average velocity was 60 miles per hour, then I know that there is some point in time where my speed was exactly that, my instantaneous speed was equal to 60 miles per hour. Now, for me, that's not going to be a huge issue because that's the speed limit on most of, or on some sections of 294 at least, 60, 65, depending on where you're at. Let's say, though, that in my two tolls that I'm measuring, my average speed was 80 miles an hour. That suddenly means that at some point in between those two tolls, my instantaneous speed was exactly 80 miles an hour. That's enough for me to get a speeding ticket. State police could monitor that for whatever reason, and they could bring that to court, and that's justifiable evidence that at some point in there, I was going exactly 80 miles an hour, which is breaking the speed limit. So that's what the mean value theorem is. It's a way of connecting an average rate of change with an instantaneous rate of change at some point in the interval. Now, there's an important result that I mentioned that we're going to get to, and that's this one here. So here's our big result. This is going to help us find intervals where a function is increasing and decreasing. So let's pretend that we've got a function f that's continuous and differentiable on some open interval I. We don't know what the interval is. We don't really care. If the derivative, f prime of x, is positive for all x in I, remember that's x in I, that's what that symbol means, then we could say that f is increasing on that interval. And similarly, if the derivative is less than 0 for all x in I, then f is decreasing. So let's first just talk about what this means. It means if we want to find intervals where our function is increasing and decreasing, the first derivative can give us clues about that. If the derivative is positive or the derivative is negative, we'll be able to use that to tell us some stuff. That's something that we'll use a bunch going forward. Let's prove that we're allowed to do this, though. So here's our proof. What we're going to do is we're going to just pick two random distinct points in our interval. So pick 2 points in I. We'll call them A and B. And just so that we're all on the same page, we're going to make A the small one and B the big one. Doesn't really matter. We could just switch the names around, but whatever. Then, by the mean value theorem, we could look at the rate of change between those 2 points that we've picked, and we could say that this is exactly equal to the derivative. And this derivative is just the derivative evaluated somewhere between there. So we'll say for some c in between A and B. Another way of writing this is saying f prime of c times, maybe I'll write it this way actually, sorry. F of b minus f of a is going to equal f prime of c times b minus a. I've just multiplied the denominator out. So this is true for some point c and for two random points a and b. But since a is less than b, that means that this thing here is positive. And so if this derivative is also positive, then we have a positive times a positive, which is positive. So that means that f of b minus f of a is greater than 0. Now, why is that helpful? That's helpful because, sorry, I'll leave this here, because then what we can say is that f of b is bigger than f of a. So f of b is bigger than f of a. So what we've done is said for any a less than b, f of a is less than f of b. And this I probably should say in I. So for any pair of x values where one of them is bigger than the other, the corresponding y values have the same ordering. This is literally the definition of increasing. So f is increasing on I. Notice if we went back and we said this derivative was negative instead, then we have a negative times a positive, meaning the whole thing is negative, meaning f of b minus f of a is negative, meaning f of a is bigger than f of b, and that would be our definition of decreasing. So that's our proof. We'll use this result. It'll be really helpful for us. Essentially what this says is that we can use the first derivative to tell us where our function is going to be increasing and decreasing. We'll do that a little bit more next time.